Okay, hello everyone. Today we will learn about continuous random variable number 4 and we will learn about gamma distribution and related families of gamma distribution such as exponential distribution. Okay. The gamma probability distribution is defined this way. A random variable y is said to have gamma distribution with parameter alpha and beta. And here, each parameter alpha and beta, they both are greater than 0. And the density function is defined like this. And in the density function, there is this gamma function, gamma alpha, and this gamma alpha is defined this way, and this one, if alpha is integer value, if alpha is integer, like alpha is any integer n, then this is n minus 1 factorial. We can calculate it. And actually, I will show you later in the later slide why this is true. And here we call alpha as a shape parameter, and beta is a scale parameter. And when y follows the gamma distribution, we say it y follows gamma, alpha, comma, beta. Okay, and in okay, next, let's go. Okay, now let's look at how the distribution looks like. The random variable y is defined on 0 to infinity, and the shape changes like this. The alpha is a shape parameter. It determines the shape. So here, if the shape is low shape, is red and green represent low shape, red and green. It's skewed to the value 0, and if the shape parameter alpha have high value, it's more extended to so green and black, we have higher shape parameter alpha. And for the scale parameter, if we have low scale and high scale, for red and green, the red one have low scale and green one have high scale. Uh, so this is how the gamma distribution looks. And one of the important trait is that except when alpha is 0, alpha is 1. When alpha is 1, it is exponential distribution. Except that case, it is impossible to obtain areas under the gamma density function by direct integration. So here's the gamma distribution, and integrating it from C to D. Actually, this is probability of y is greater than or equal to C and less than or equal to D. Okay. This is the direct integration is impossible. Okay, and so how we can calculate this value? To do that, you can computationally calculate that number. So using R software with your computer, you can generate the probability of y is less than or equal to y0 using this command, p gamma. And actually, this is p gamma. P gamma, y0, alpha, and 1 over beta. Then you can calculate, let's say this is a gamma distribution, and you can calculate this probability using p gamma, y0, alpha, 1 over beta. And if you use the function q gamma, then you specify pth quantile. So So in this case, here if you want to have 50th quantile, like 50th quantile, 0.5, then if you want to find the median, then the area of this is 0.5, and this position is 5p. 5p. Actually, this is 5.5. So you can calculate the median using Q gamma function. Q gamma 0.5 and alpha and 1 over beta. Okay, so this is how you can get the probability densities, probabilities related to gamma distribution. Okay, before we go on, let's learn about the gamma function. So gamma is defined like this, and here actually the gamma when gamma 1 is 1, why is it true? So for gamma 1, gamma 1 is from 0 to infinity. E to the minus y dy, and this is minus e minus y from 0 to infinity, and this is e to the minus infinity, which is 0. So 0 minus minus, which is plus, e to 0 is 1, and so this is 1. So gamma 1 is 1. And what about gamma 2? Gamma 2. Gamma 2 is from 0 to infinity, y e to the minus y dy. And here this is from here, let's let u equals y, and we derivative as e to the minus y, and then u prime is 1, v is minus e minus y. Okay, and now this is uv from 0 to infinity minus integration from 0 to infinity u prime v dy, and this is from 0 to infinity y minus e to the minus y, and minus from 0 to infinity minus e to the minus y dy. And from here, this part, this part is this one. Okay, so yeah, here this part, if we put infinity, minus y times e to the minus y, and actually this part can be represented as e to the minus y plus actually the y is e to the log ln y, and so y is e to ln y, and e to the ln y times e to minus y, that's e to minus y plus ln y. And here, as y goes to infinity, this part increases slowly. So this the full part go to negative infinity. So this part becomes 0, so this part is 0 when y goes to infinity, and this part goes 0 again. If you put 0 in here, the y times e to the minus y, if you put 0 to y, then this part is again 0. So 0 minus 0 is equals 0, and the other part from 0 to infinity, e to the minus y dy, and this part is actually gamma 1. So this is gamma 1. And actually, for the general case, if you calculate it as y to the n minus 1, y to the n minus 1, e to the minus y dy, and if you put your u as y to n minus 1 and v prime as e to the minus y, and if you put y prime as n minus 1 y n minus 2, and v is minus e to the minus y, and if you derive something, then you can prove that this is n minus 1 times gamma n minus 1. So what you can prove is that gamma n, and if n is integer, then you can prove that gamma n is n minus 1 factorial. This part I skipped some steps. I think if you put these u and v's this way, you can derive the y gamma n is n minus 1 factorial. Okay. Let's move to theorem 4.8. If y has a gamma distribution with parameters alpha and beta, then mu, expected value of y, equals alpha beta, and sigma square, variance of y, is alpha times beta to 2. Okay, and here to prove this, expected value of y is sigma from 0 to infinity y times py, and the py is beta to alpha, gamma alpha, and y to alpha minus 1, e to minus y over beta. Okay, and from here, this is actually from 0 to infinity, y to alpha, and e to minus y divided by beta, and beta to alpha, and gamma to alpha. And actually, we want to use this one. We want to use this integration of y alpha minus 1 times e to the minus y divided by beta, and beta alpha, gamma alpha, from 0 to infinity. This is 1. So what we want to use is that we want to use this one. What if alpha is increased by ones, like y alpha e to the minus y divided by beta divided by beta to alpha plus 1 and gamma alpha plus 1. This is again 1 because this is when y follows gamma distribution alpha comma beta, and here for this y follows gamma distribution alpha plus 1 comma beta. So this is again gamma distribution, so the sum of this distribution is 1. So what we want to use from here is and what we also know that gamma alpha plus 1, this is alpha times gamma alpha. So here times alpha and divide by alpha, and actually we can put it here, times alpha here and alpha here, and also here times beta here and times beta here. Then this one becomes alpha times beta, and the integrating part from 0 to infinity, the inside part is beta to alpha plus 1, gamma alpha plus 1, and y to alpha e to the minus y over beta, and dy, and this is this y follows gamma distribution with parameter alpha plus 1 and beta. So this is the integration of this is 1. So expected value of y is alpha times beta. Okay. Okay. So the next one is the variance part. So we want to calculate variance of y. To do that, we usually use this formula, expected value of y square minus ey square. And so we want to calculate this ey square. So to calculate ey square, and this is integration from 0 to infinity y square, and here we have y to alpha minus 1 and e to the minus y divided by beta, and here beta to alpha and gamma alpha. And here, in here, if we put y inside, then this is y to alpha plus 1 and e to the minus y divided by beta, and here to match this, we want to use gamma alpha plus 2 comma beta distribution, the distribution of this the integration from 0 to infinity for this distribution is 1. To use that, for now we have beta to alpha and gamma alpha, and to use this one, we want to put gamma alpha plus 2 and beta alpha plus 2. So to do that, this gamma alpha plus 2 is alpha plus 1 times alpha times gamma alpha. So we can multiply this outside. So this is beta second times alpha times alpha plus 1, and for the integration part, from 0 to infinity, y to alpha plus 1 e to the minus y over beta, and here beta alpha plus 2 and gamma alpha plus 2 dy. Okay, and here, since this one follows gamma distribution, this thing, the integration of this is 1, so this is beta square times alpha plus 1. Okay, this is ey square, and since ey is alpha beta, so ey square is alpha square beta square. So vy is alpha square beta square uh, plus uh, alpha beta square minus alpha square beta square, beta square. This one cancels, so the variance of y is alpha times beta square. Okay. Now here comes the definition 4.10. Let v be a positive integer. A random variable y is said to have a chi-square distribution with v degrees of freedom if and only if y is a gamma distributed random variable with parameter alpha is v over 2 and beta equals 2. And Mm, actually, for the chi-square distribution, we will cover it later, and it have relationship with normal distribution. So if z follows standard normal distribution with mean 0 and deviance 1, then the z square this follows the chi-square with degrees of freedom 1, and if we have multiple sum of z squares, like sum of I equals 1 to k and z I square, this follows chi square k, and these zi's are IID normal. If this relationship hold, then sum of z squares follows chi square, and the z square follows chi square 1. And we will learn in the future, so I will not explain the details about the chi-square distribution, but what I want to say here at this point is that the chi-square distribution is a special case of the gamma distribution. So from the gamma distribution, if we set our alpha as v over 2 and beta equals 2, then that's the gamma distribution. Then that's the chi-square distribution. So chi-square distribution is a special case of gamma distribution. That's the important thing here. Okay. And for the mean and variance of the chi-square distribution, and this can be derived from the gamma distribution. So the expected value of y is v, and variance of y is 2 times v. Since we already calculated mean and variance of gamma distribution, and the chi-square distribution, it is special case. So ey, it is alpha beta, and variance of y, it is alpha times alpha square beta. No, alpha times beta square. Okay, so if you put alpha and beta, alpha as v over 2 and beta equals 2, then you will find that expected value of y is v and variance of y is 2v. Okay. Now let's move on to definition 4.11, which is about exponential distribution. And exponential distribution is also a special case of the gamma distribution. So if we set alpha equals 1 from the gamma distribution, if we set alpha equals 1, then it is exponential distribution. So let's check. So for the gamma distribution, it is y times alpha minus 1, expected value of minus y over beta, and uh, beta to alpha and gamma alpha. And from here, if we put alpha equals 1, then the it is expected e2 minus y over beta and divide by beta, since gamma 1 is 1. So this is this one. Okay. And one of the important property is that this exponential distribution is continuous analogous of the geometric distribution, in that it has the key property of being memoryless. So both gamma distribution and geometric distribution have memoryless property. I will explain it in the later slides. And for this exponential distribution, the expected value of y is beta, and variance of y is beta square. And we say if y follows exponential distribution, we describe it as y follows exponential distribution with beta. Okay. The next example 4.10, is actually about the memoryless property. This equation is called memoryless memoryless property, in that um, mm, and this one can be thought as memory, like y, the random variable y is greater than a. However, this memory do not necessary for calculating this probability. The probability of y is greater than a plus b, given y is greater than a, can be simplified as probability of y is greater than b, which is this if we have knowledge that y is greater than a, if we have that kind of memory, this information is not necessary. So this is why this is called memoryless property. And let's prove this for the exponential probability density. Okay, so yes, for exponential probability density, this is 1 over beta times e to the minus y over beta. Okay, so probability of y is greater than b. This is from b to infinity, 1 over beta e to the minus y over beta dy, and this is minus e to minus y over beta from b to the infinity, and this is e to the minus infinity. This is 0, so this is e to minus b over beta, b over beta. Okay, and and probability of y is greater than a can be also calculated as e to the minus b over ra. Okay, and probability of y is greater than a plus b. This can be also calculated as e to the minus I think e to the minus a over beta, and here this is minus a plus b over beta. Okay, so the probability of y is greater than a plus b given y is greater than a. Actually, this is probability of y is greater than a plus b divided by probability of y is greater than a, and this is e to the minus a plus b over beta divided by e to the minus beta a, and this is e to the minus beta a plus b plus a, and this is e to the minus b over beta, and so this is same as this one. So this is probability of y is greater than b. Okay, so this is proof for example 4.10, and this is proof for memory list property of exponential distribution. And okay, the memory list property also holds for geometric distribution. So let's say y follows geometric distribution with p, and then the probability density, probability math function for this, it is p times 1 minus p to the y minus 1, and here y is defined from 1 to okay, and the memory list property is that probability of y is greater than a plus b given that y is greater than a. This is same as probability of y is greater than b. Okay, we want to show this memory list property, and to show that we calculate the probability of y is greater than let's see, b first. Then this is sum of y is from b plus 1 to infinity, and p times 1 minus p to y minus 1, and for this one this is infinite series of the infinite geometric series. So this is the first value is p times 1 minus p to b, and over this part is 1 minus 1 minus p, and this is p, so this p cancels, and this is 1 minus p to b. Okay, and similarly py is greater than a is 1 minus p to a, and also probability of y is greater than a plus b is 1 minus p to a plus b. And so the probability of y is greater than a plus b, given y is greater than a, and this is probability of y is greater than a plus b divided by probability of y is greater than a, and this is 1 minus p a plus b divided by 1 minus p a, and this is 1 minus p b, and this is the probability of y is greater than b. So this is proof for the memory list property of geometric distribution. Okay. And homework for the gamma distribution are these.